look. At the world. Now, this is from the Shuttle Radar Topography Mission data. This is relatively incomplete data. You'll notice that it doesn't extend past 60 degrees north or south latitude. But this is one of the more accurate surveys of world topography that we have. Now, several people have asked as we start looking into faults, is there a preferred type of fault? Is there some dominant style of fault? And so I thought it worthwhile just to take a look around the systems and look at some of the fault systems we are going to describe. If we look here, let's start with Africa. If we look along this western margin of Africa, this is a normal fault dominated system, where we have here several normal faults stepping out into the Atlantic. This zone in here is a little bit of an extension and strike slip system here. These basins correspond to the basins along South America. There is almost a perfect agreement between the basins off of Brazil, the Santos Basin, which is their most prolific oil and gas basin, and basins that we find off of Angola. And so these two are almost a perfect match. This is almost a perfect match there, where we have extension and some shear in that particular system. If we look in here, we have Red Sea, Gulf of Aden. This is a massive extensional system where this has opened up over the past few 100,000 years. You're looking here at the East African rifts. In here, Madagascar has moved off of here. This would be a normal fault type of a system. So normal, normal, normal. Then when we look at this particular map, if you look, let's start over in here. In Indonesia, this would be Sumatra, this would be Borneo. This is Sulawesi, Halmahera. This would be Papua New Guinea, Irian Jaya. That system here is dominated by thrust faulting. As we come up into Malaysia, up into Burma or Myanmar, this is all thrusting in this area. All this complex is thrusting up in that area. The thrusts bend, come around. Here we are in the border between Afghanistan and Pakistan. This is a massive thrust system here, all the way over into Iran, where we have the Zagros Range. That is a thrust system coming over into Turkey. That is thrust system here. It extends, look at this weird bend in here. That is all thrust through there. If we come over into this is all thrust on this margin here. Thrust fault dominated, so one boundary is normal fault bounded. This one is thrust fault dominated. Most of this is thrusting in here. We have the Central Cordillera, which is thrusting, and we have this unusual place here, which is extension. And so it seems to be almost an even match between thrusting and extensional systems. There are some massive strike slip faults in the world. If we look now, New Zealand does not show up, or did I just zoom in too much? Let's go back. Oh, New Zealand barely shows up over here. There is a massive strike slip fault that cuts through here in New Zealand. That is the Alpine strike slip fault. There is a massive strike slip fault that cuts right through here. That is the Anatolian. You have a northern and southern Anatolian zone. The last earthquake that occurred in this region was 1999 in Izmit. Roughly 30,000 perished in that earthquake. We have massive strike slip faults in here. we have a massive fault that cuts through here. It's called the Red River Fault Zone that cuts through into northern Vietnam, and that is a strike slip fault zone. We have the Tan Shan that extends over here. There's another massive strike slip fault that extends here. And we have the San Andreas that extends up in there as the major strike slip fault zones in the world. And so what we're going to do over the next few days, we're going to look at faults and fault systems around the world, and we're going to look at them in some detail. So here we've zoomed in a little bit into Eastern Africa, the East African rift systems. And so just for location, can you locate Madagascar? Okay, so Madagascar's down here. This would be Somalia. This would be Djibouti and Eritrea here. This would be the Arabian Peninsula in here. So Yemen would be up in here. Saudi Arabia would be further up in there. Egypt is over in here. And so we come down. This is the East African Rift. There is a western side to the rifts that cuts down through here, comes out through Malawi, down, out. We have another one that cuts in there, over. So this interesting little triangle will eventually be an island, just like Madagascar. And we have an eastern here. This would be Lake Victoria, right in there, Kilimanjaro, so that we have a massive rift system in East Africa. We want to try to understand the geometry of those rifts. We want to try to understand how those normal faults developed over time in that system. But the key thing to notice is that these are relatively narrow, rift-bounded grabens in that setting. If we compare to what we see, oops, we're going the wrong way on this one. Let me pull the other one up. There. If we compare to this, which is the western part of North America, this is in the western US in this particular case. Just for reference, if you've seen the Grand Canyon, this is the Grand Canyon right there, this little bitty thing. That is the Grand Canyon. This is a massive sequence of structures in here. What you're looking at is the basin and range province of western North America. And in this case, this is an extensional zone that's experienced probably close to 600 or 700 kilometers of extension in that system, giving you this classic basin and range topography in that system. And so we want to understand the difference between the narrow rift valleys in Africa and this larger scale extension in here. And you'll notice there's this kind of odd lineation down here. This is Walker Lane. That is a shear zone, a strike slip system that is occurring here in that particular system. So massive extension in this system, and in Africa we have relatively narrow faults. So when we look around the world, we can actually see a tremendous array of different geometries. Here we're back in Asia. Here this would be India. Here this would be the High Himalaya. This would be Kashmir region right in there. This is the Tibetan Plateau. This is the Tarim Basin in here. This feature right there is Lake Baikal. Lake Baikal contains roughly 20 to 22% of the world's fresh water supply in a single lake. The lake is roughly 1 mile deep at its deepest point. It is a sharp fault-bounded system, normal faults Yeah, 10.
What was the percentage of the fresh
About
water?
20 to 22% of the fresh water in the world is right there in Lake Baikal. It's probably the deepest freshwater lake in the world. It is a rift, normal fault-bounded lake in that system. And as we begin to investigate these systems, what we will realize is that in this particular case, Lake Baikal is India's fault. India colliding with Eastern Asia caused Lake Baikal to form. If you look here, India has pushed this distance, in some cases approaching 700 kilometers into Asia, here causing the uplift of the Himalaya, the uplift of the Tibetan Plateau. In that system, we have basically squeezed China out into the Pacific since that collisional event began, along these great transforms, the Red River here and the Tanshan up here. That continues on up where this has rotated and split out along that strike slip between here and here. So this has been pushed out. This has been pushed out due to the collision of China and India, or Asia and India. And so this is our member that is actually pushing into, and still actively pushing into, Asia, that transform, that one, causing Lake Baikal to form. So we want to look at how these systems behave. We want to try to begin to integrate a world model into our heads. Can we look at these systems? Can we look at the world and begin to interpret the structural style from imagery even as remote and coarse as this, where we can look at this and begin to reconstruct the entire history? The answer is yes, we can. We can really start piecing together the entire planetary history and the history of specific regions just by looking at this type of remote sensing and understanding a little bit about normal faults. So, let's begin. When we think about normal faults, one of the key things that we want to understand is that this idea that I have a normal fault system where the faults are just these stick straight things and we down drop like this. This is, I guess to be blunt and politically incorrect, this is ridiculous. This we see only on the smallest scales. So if we go back to the entrance of Arches National Park near Moab, there's a great Mexican restaurant in Moab, by the way. You look at that and you see these stick straight faults. So in this particular case, you will see those things at a reasonably small scale. But when you get into larger scale systems, what we find is that faults must curve so that the geometry is going to be more Listric. So what we should realize is that, number one, faults must curve. We're on a sphere. We're breaking things, we're moving things, displacing things on a sphere, so they have to have curvature to them. And I guess you could have this as a demonstration motto: faults must die out. They're not infinite. Faults cannot be infinite. If faults were infinite, we would have a very strange universe. If faults were infinite, we would have a very strange planet, because if we offset 100 meters here, we would have to offset all the way through the planet and have an offset of 100 meters on the other side of the planet. Not going to happen. Faults occur only near surface, so they actually must die out. That means the displacement on the faults must die out as well. So it's possible to have a fault that in some areas might have 100 kilometers of displacement, and in other areas have that displacement go to 0, which is a tough thing to get your head around as we begin to think about these faults. So let's look at a Lystric normal geometry. When we think about, these are always gross, when we think about a Lystric geometry, what we're saying is that as we have worked on faults and fault systems, as the literature has been developed, people began to realize that this stick-straight model that you saw in physical geology just didn't work. They could not reasonably balance out those geometries with the observations that they were making. And so what we found out was that faults tend to flatten with depth. So that if we look at a fault system, a normal fault system, the geometry started to look much more like this, where we had some level at which the fault began to flatten. It's a curved geometry, where the dips up here might be on the order of 70 degrees. The dip down here tend towards 0 degrees in that particular system. This is a Lystric geometry. Now, no scale. There's no scale on here yet, because you can see this at relatively small scale. You can see this in the Gulf Coast. Some of the deep plays in the Gulf Coast are taking advantage of this type of geometry. Some of the deep plays that you have in the Niger Delta are taking advantage of this geometry. So if you go into oil and gas exploration, production, engineering, and you end up in the Niger Delta, you're going to be playing with a Lystric normal fault system that has some pretty intriguing reservoirs. If you look at the geometry of the reservoirs that you're going to be exploring offshore Angola, you're going to be playing with this type of geometry. If you've worked in Brazil offshore, again, you're going to be looking at this type of geometry. The scale will depend on the material that we have. So if it is a relatively weak material, that will be small. If it is a relatively strong material like crust, it will be large. If we're dealing with lithosphere, let's look at, okay, that's a big word. Do you guys know what lithosphere means? Do you remember from physical geology? What's the definition of lithosphere? Again? The upper part of the Earth's system. If we look at a simplistic pie slice of the Earth, how big would the lithosphere be? So here we have a complete slice of Earth. We're going to take the Earth, cut it in half, take a pie slice of that, make a pizza out of it. So in this particular case, how thick would the lithosphere be at that scale?
10 kilometers.
Well, at this scale, we couldn't see it. The lithosphere extends basically from a temperature zone of about 1200 degrees centigrade up to surface. It includes part of what we would, in old terminology, would have called the upper mantle, and it includes part of what we would call the crust. The average thickness of the lithosphere worldwide is right about 30 kilometers. Average. It can be as thick as about 85 kilometers if you look at some of the shield areas like the Canadian Shield, Rhodesian Shield, Baltic Shield, Siberian Shield, about 85 kilometers. It can be as thin in areas, if we go out into the mid-ocean systems, that can be as thin as just less than a kilometer. So it varies widely. The behavior of the lithosphere, particularly continental lithosphere, is unique. If we look at continental lithosphere, we find out some intriguing things. If we take a look at continental lithosphere here, so we're going to say this is 1200 degrees centigrade. This is our surface here. This would be an average. Let's say that this in this particular area of the United States, we're looking at 40, I think 40, 45 kilometers. What we find is that the upper part of this is brittle. It will fracture, it will break in that system. The lower part is an interesting combination of viscous and plastic behavior. It does not break. It can flow, but it's not going to fall. So what that says is that when we start looking at these large-scale rift systems, these large-scale extensional systems, everything is happening up here in this brittle zone. Everything is happening above a depth on average of about 10 kilometers. That is what we call the brittle ductile transition zone. Oops, there's an N missing. That brittle ductile transition zone occurs at a depth of about 10 kilometers. So these normal faults that we have been drawing as these stick straight diagrams in physical geology, don't blame Dr. Cornell, are right. They curve, they flatten with depth, and they will tend to flatten out at a depth of about 10 kilometers. That means that if we take lithosphere, so here we're going to grab a piece of the lithosphere, we're going to take it and we're going to stretch it. We're going to cause it to fall. This lower part behaves plastically. The upper part is going to behave more brittly and is the system, the zone that faults and breaks. And so what we're going to try to understand is the geometry of rift systems like we see in East Africa. East Africa is absolutely the best place in the world to examine rifts and rift systems. And then we will try to understand these large-scale extensional fault systems that we see in the western United States. And that will include some bizarre things like metamorphic core complexes that are glorious little monsters. If you ever happen to go to Reno, Nevada, go north of the casinos into the University of Nevada at Reno. If you go to the geology department and park in their parking lot, you're in a metamorphic core complex. That may have been by design, because when you look at the wall of the parking area, you see these beautiful high-grade metamorphics that are sheared out. You're in an absolutely fabulous metamorphic core complex. So we need to begin to understand this system. We need to eventually fill that diagram in. because there's not much information there now. We want to try to understand what the interior of the Earth is behaving like, because ultimately, what is going to control the structures that we see is happening down here. This is where the vast majority of the activity that generates the structures is on there. All right, see you guys on Wednesday. We will continue with normal fault and normal fault system.